I'm sharing my screen. One second. One second. First we'll see the short channel effect. Okay. First we'll see the what is the short channel effect. We'll see. Okay. So short channel effect. Why these short channel effects are happening? Means nowadays we are in different technology, no. So that means we are in. So previously, like last 10 years back, we are in 220 nanometer technology and 90 nanometer technology, 45 nanometer technology. So what is this technology? Technology is nothing but what? Technology is nothing but the length of the channel. Length of the channel. So we already seen the MOSFET, no? So MOSFET you have source and drain. So the length of the channel is nothing but technology. Okay. So that means day by day there is a Moore's law. I told you about the Moore's law. So Moore's law given a statement that transistor count doubles for every 18 to 24 months. So what happens means now we are working under what we call so we are working under 3 nanometer and 2 nanometer technology. Okay, 3 nanometer and 2 nanometer technology. Okay, so day by day, so what happens day by day, the transistor channel, so the channel length is decreasing. Okay, so when the channel length is decreasing, we'll get some problems when we integrate these MOSFET circuits within an IC. Okay, those are nothing. Five different physical phenomena are considered. These are nothing but we can consider as a problems. Okay, or challenges. Okay, so what are the challenges? Are nothing but these challenges are nothing but short channel devices. Okay, so these are nothing but short channel devices. So there are total five short channel devices are there. So one is drain induced barrier lowering and punch through. Okay, drain induced barrier, so this we call as DIBL. Okay, DIBL. Okay, so DIBL is nothing but drain induced barrier lowering and punch through. Okay, that is nothing but punch through. And one next one is surface scattering, and next one is velocity saturation, and next one is impact ionization and hot electron. Okay, so when you are going to the tool class also, so mostly you come across these short channel effects and velocity saturation, hot electrons and all those things. Okay, so before that, before going into the tool classes, you need to know the idea what are these. Okay, so coming to DIBL. Okay, drain barrier. So what is this? Drain induced barrier lowering. Okay, drain induced DIBL. So the drain induced barrier lowering. Okay, drain induced barrier lowering means in the MOSFET we already seen. That means so when the so if you take enhancement n channel MOSFET. Okay, enhancement n channel MOSFET. Okay, so n channel MOSFET. Okay, can anyone say the difference between enhancement and depletion? Did you remember? What is the difference between enhancement and depletion MOSFET?
Rather in enhancement, we create the channel.
Enhancement MOSFET, there is no channel, so we need to induce the channel, we need to create the channel. And depletion MOSFET, already channel is there, and this depletion MOSFET is operating in both what we call both in enhancement and depletion. Okay, so that means enhancement means we can increase the electrons in the channel, and depletion means we can decrease the electrons in the channel. Okay, so coming to the enhancement MOSFET, so when the channel is formed, enhancement n channel MOSFET, when the channel is forming, when VGS is greater than VT only, we discussed about weak inversion layer and strong inversion layer. Okay, so weak inversion layer is nothing but channel is not forming, the number of electrons present in the channel is less than the number of holes in the p-type substrate. Okay, so when the strong inversion layer channel is forming means when VGS is greater than Vt such a way that the number of electrons in the channel equal to number of holes in the p-type substrate. Okay, and this is nothing but we call as channel formation. Okay, channel formation. This we already seen in the CMOS MOSFET character MOSFET operation. And next we are increasing the VDS, no. So next we are increasing the VDS means what? So that means again it is operated in a linear region, non-linear region, and next saturation region. So that is depending on which one means. When VDS is less than VGS minus VT, it is operated in linear region and non-linear region. Okay, so that means first you will get linear region. After that, the amount of gate voltage that will decrease, and here you will get the channel will be pinch off. That is pinch off condition will get when VDS equal to VGS minus VT, and saturation means the current become constant. So that means this become constant. So when VDS is greater than equal to VGS minus VT. Okay, so what happens here, as you increase more and more we already seen. So as you increase more and more VDS, so here if you see, this is source and this is drain. Okay, this is drain. So channel will be this is not much, channel is pinched off, and as you increase more and more VDS, okay, drain to source voltage, so VDS, what happens, this will be like it will be moved from drain to source, no. It will be moved towards drain to source. Okay, so this is nothing but, I told you, this is nothing but drain current become constant, and this is nothing but we call as punch through. Okay, that is nothing but channel will be moved towards from drain to source. That case is nothing but we can call as punch through or reach through. Okay, so that means the what we call whatever the channel is there. Okay, so this channel going from drain to source, the depth of the channel, that means whatever the depth of the channel is depending on which one. As you increase more and more VDS, there is a reduced channel. Okay, and a reduced channel, and there is a barrier lowering means so initially channel will be uniform, and after that channel becomes a non-uniform, and after that what happens, there is a channel lowering, barrier lowering. Okay, so this is a channel barrier lowering. Okay, so that means this is nothing but DIBL. Okay, so DIBL is nothing but drain induced barrier lowering, that we call as punch through. Okay, that is nothing but, so that means still you increase the VDS more and more. Okay, still you increase VDS more and more, channel will be breakdown. Channel will, what happens, channel will be breakdown, and current will flow. Current becomes constant only, but channel will be breakdown occurs in the channel. Okay, so what is breakdown means, there is no connection between the channel between drain and source. The channel move from where to where means drain to source. Okay, so this is nothing but breakdown condition. Okay, so this condition is nothing but breakdown condition. Okay, so this is nothing but DIBL. Okay, DIBL, that is nothing but drain induced barrier lowering and punch through. Okay, drain induced barrier lowering and punch through. Okay, so this is a DIBL. And next you see surface scattering. So what is the surface scattering means, as you increase as you increase VDS more and more, as you increase VDS more, still you increase VDS more and more, no channel electrons will move across the surface. Okay, so that means as you increase more and more, so there is across the surface of this one. So what happens, this is source, and this one is drain. Okay, as you increase the VDS more and more, the channel will come here. Okay, so no more electrons will be flowing toward this surface. Okay, why? Because due to more mobility. Okay, due to more mobility and electrons with high electric field. Okay, so due to this electrons with high electric field, so no more electrons will move across the surface, this surface of the substrate. Okay, so there is no path for the electron to pass from where to where, source to drain. Okay, source to drain. One second, please. Yeah, okay, yeah. Okay, so this is nothing but surface scattering. Okay, so this is nothing but we call as surface scattering. Okay, see here, so that means here so this is the diagram. There is a inversion layer is there. Inversion layer means what? So inversion layer means normally this is a p-type substrate, but actually the channel is forming due to electrons. Okay, a n-type like material is forming on the surface of the substrate. This is nothing but we call as inversion layer. Okay, so as VGS is greater than VT, channel is forming and electrons will be flow from where to where, drain to source. So as electrons are flowing from drain to source, there is a conventional current. The current will flow from source to drain. Electrons will flow from source to drain, and the current will flow from drain to source. Okay, this is nothing but depletion layer. So how the electric field is occurring towards, this is Ex. Okay, this is this is the epsilon x. Okay, permittivity of this silicon dioxide. Okay, say what, or channel, like that we can consider. Okay. So this is the diagram, and once again surface scattering. Yeah, next is velocity saturation. Velocity saturation we seen, surface scattering we seen. Okay, velocity saturation means the electric field in y direction. Okay, that means you are applying VDS. Okay, that means you are applying VDS. Okay, VDS positive means with respect to source and drain you are applying positive voltage. Okay, so you are applying positive voltage, and next what you are doing, you are increasing more and more VDS. Okay, so due to this voltage what happens, there is an electric field. Okay, electric field in which direction? Y direction. Okay, so this is nothing but electric field which is happening, this one, see here, this is the electric field in the y direction, Ey. Okay, so electric field in the y direction, as VDS increases. Okay, as VDS increases, electrons velocity increases, and it will crosses the conventional velocity. Okay, there will be some conventional velocity there, so conventional velocity of the electron will be there. So as you increase more and more VDS, so this electron velocity will increase, and this crosses the conventional velocity. So what is the conventional velocity? So conventional velocity is increased by 10 power 4 volt per centimeter, but this drift velocity, okay, drift velocity we already seen in the PN junction diode. No, there are, that means drift current, drift velocity, that means when you are applying the electric field, there is a motion of electrons are happening. Drift current also we already seen, that is due to electric field. Okay, diffusion current also we seen, that is due to concentration gradient. Okay, so drift velocity approaches the saturation velocity. Okay, so what is that value means 10 power 7 centimeters per second. So this is nothing but 10 power 7 centimeters per second. Okay, this is nothing but velocity saturation. So velocity saturation in simple way you can say that as you increase more and more VDS, electron velocity increases. Electron velocity increases, and it crosses the conventional velocity of the electron. Normal velocity, conventional velocity is nothing but normal velocity of the electron. Okay, so that means velocity of the electron increases, and it crosses the conventional velocity of the electron, normal velocity of the electron. That is nothing but velocity saturation. And next is impact ionization. What is this impact ionization means?
Sir, what is the value?
This is conventional velocity of electron is 10 power 4 volts per centimeter, but normal drift velocity is 10 power 7 centimeters per second. Normally, this was drift velocity. Okay.
Yes, sir.
Next, impact ionization. What is this impact ionization means? Presence of high longitudinal fields can accelerate the electron that may be able to ionize the silicon atom, may impact against them. So what is the meaning of ionization? Can you say, anyone say what is the meaning of ionization? It will ionize the silicon atom. Okay, normally due to this high longitudinal fields, so these electrons, whatever the electrons are there, that will accelerate. okay, that will accelerate, and that can able to ionize the silicon atoms, okay. So so you have silicon atom, no? So that can ionize the silicon atoms, and there is an impact on silicon atoms, so that is nothing but impact ionization, okay. uh, so mostly most of the electrons are attracted by drain, so it is possible to higher concentration of holes near the source, okay. So mostly when you are applying VDS, electrons are flowing from where to where? Source to drain. Electrons are flowing from source to drain, okay. So so in order to overcome this impact ionization, so we need to we need to make uh, higher concentration of holes near the source, okay. Near the source we need to make higher concentration of holes, okay. So this hole concentration in the source able to create the voltage drop on the surface of substrate, and so this is about 0.6 volts, okay. So this is about the impact ionization. So that means due to what we can say, that means impact ionization means due to longitudinal fields, what happens means this electrons will accelerate more, and that can ionize the silicon atoms, okay. So there is an impact on the silicon atom, that is nothing but impact ionization, okay. So this is the impact ionization, okay. So due to this impact, the means electron is acquiring some acceleration, no? Electron is acquiring some acceleration as you increase more and more VDS voltage. What happens means this electron is there, no? This electron can inject from source to substrate, okay. So this electron is there, no? So electron acceleration is increasing, and electron can inject from source to substrate, okay. It can inject from source to substrate, okay. Or it can flow like this also, it can flow into this silicon dioxide also, okay. It can go into the silicon dioxide also. When it will go into the silicon dioxide, when it is injecting into silicon dioxide, the electron become hot electron, okay. The electron become hot electron. See here, electron may inject from source to substrate, or electron travel the drain, increases their energy and create electron hole pair, okay. So that means so here electron hole pair means suppose electron is passing towards the substrate, what happens due to this acceleration, already holes are there, so these electrons will combine with the holes, and this will make for electron hole recombine, okay. This is make a combination, okay. They will recombine and they make a electron hole pair, okay. They make a electron hole pair and they will disappear, okay, due to impact ionization, okay. So that means here, see here, electrons may inject from source to substrate. So in substrate, what are the majority carriers? Holes. We are using P substrate, no? We are using P substrate, the majority carriers are holes. So electrons toward the drain increases their energy and create what? Electron hole pair, okay. So electron may escape the drain field and affect other devices also, okay. So that means it is escape from the drain field. So normally it should flow from where to where? Source to drain, okay. So but what happening due to this impact ionization, it is acquiring some acceleration and it is moving towards the substrate, okay. That is it is changing its trajectory, okay. So that is due to impact ionization, okay. That is due to impact ionization. And next, hot electron. What is this hot electron? Channel hot electron effect is caused by electron flowing in the channel for large VDS, okay. So what happens means here you have electrons, okay. So electrons acquire so much energy and it will flow toward the this SiO2 layer, silicon dioxide, okay. So SiO2 layer, when it is going into this silicon substrate, so what happens, electrons arriving at silicon and silicon dioxide interface with enough kinetic energy, okay, with enough kinetic energy, okay, and it will be injected into the oxide, okay. When it is injected to the oxide, that electrons we call as hot electrons. Hot electrons. Okay, so you have like so you have source and drain. You have source and drain. Okay, and next in between there is a channel. There will be a channel. Okay, channel is forming. Here there is a channel is forming, and as you increase VDS more and more, there is a punch through is happening. Okay, and electrons will acquire some kinetic energy, and here you have oxide, no, here you have a oxide. Okay, so electrons will be acquire some kinetic energy, and this will be injected towards this uh, SiO2 layer. Okay, so this will be injected towards this SiO2 layer. Okay, so when it becomes towards this injected to this SiO2 layer, the electrons become, we can call as hot electrons. That is nothing but we call as hot electron. Okay, so electrons arrive at silicon and silicon dioxide interface with enough kinetic energy to surmount the surface of potential barrier, are injected into the oxide. That will be injected into the oxide. That is nothing but we call as hot electrons. Okay, those are nothing but hot electrons. Okay, so these are the problems we are getting. Okay, these, so when it is going, these electrons are going into this silicon dioxide, it can degrade permanently the CV characteristics. What is CV characteristics? Normally I told you about MOS, no, MOS capacitor. MOS capacitor. So that means normally you have like so this is source and this is drain. Okay, normally why you are keeping this oxide means in order to separate the polysilicon and in order to separate the semiconductor. Okay, this is p type substrate. Okay, and here also there is a channel is forming due to electrons. Okay, so that means here this is negative and here are applying positive, so it is acting like a capacitor, no, it is acting like a capacitor only, no, in between there is a dielectric. Dielectric is nothing but what? Oxide layer, SiO2 layer. Okay, so when electrons are injected towards this SiO2 layer, what happens, you have some CV characteristics, capacitor voltage characteristics are there, that can degrade permanently for the MOSFET. Okay, so this is also one more problem. Okay, so due to this short channel effect, these many problems are coming. So one is what, drain induced barrier lowering and punch through. Okay, so that is when you increase more and more VDS, the channel is coming towards source region, and that is that we call as punch through or reach through. Okay, and surface scattering. Surface scattering means we already seen. Okay, so that means no channel, electrons will be move on the surface. Okay, there is no channel, channel is not there, so electrons will not move across the surface, that is surface scattering. Okay, and velocity saturation also. So that means velocity acquire, these electrons will acquire velocity. Okay, that increases, that crosses the conventional velocity, that is velocity saturation. And impact ionization. So impact ionization means electrons acquire some acceleration, this can ionize the silicon atoms also. Okay, that is impact ionization. Okay, and hot carrier electrons means when electron acquire some acceleration or acquire velocity, so that can move towards this SiO2 layer, silicon dioxide. So what happens when it is going toward the silicon dioxide, the CV characteristics are there that permanently degraded. Okay, so this is also one problem. So these many problems are coming when you are doing with short channel effect. Okay, so these also you need to consider. Why? Because you are going with so initially there is a 220 nanometer technology, 90 nanometer technology, 45 nanometer technology. So go on shrinking the transistor size. So now we are working under 3 nanometer or 2 nanometer technology. So when you are decreasing the transistor size, all these problems will come into the picture. These are nothing but short channel effects. Understood?
Yes.
Okay, this is charge channel effect. Yeah, 1 second. Next is CMOS latch-up. Okay, what is this CMOS latch-up? We'll see. Okay, latch-up in CMOS circuits. Okay, so latch-up in CMOS circuits means what? Means here there existence a low resistance path between VDD and VSS. Okay, there exists a low resistance path between VDD and VSS. You have CMOS circuit. Okay, CMOS circuit we already seen, no? So this is PMOS, PMOS, and followed by NMOS. Okay, and these are connected. This is connected to VDD, and this is connected to ground. Okay, so what is this CMOS latch-up means? There is a low resistance path between VDD and VSS. This is possibly with the help of virtual transistor or resistors. Okay, this leads to static current flow from VDD to ground. Okay, so due to the static current flow from VDD to ground, what happens? When it is static current is flowing from VDD to ground, our CMOS transistor may damage. Okay, CMOS transistor may damage. Okay, that is nothing but latch up in the CMOS circuit. Okay, so before going into the latch up, you need to know about the SCR. I think in BTech you studied what is SCR. Silicon controlled rectifier. Silicon controlled rectifier. Okay, what is the silicon controlled rectifier? So that means you have like a diode. Okay, anode and cathode, and there is a gate will be there. Okay, this is nothing but gate will control. Okay, so if you draw this one, so how the silicon control rectifier will look like means PN. Okay, here you have gate, PN, here you have gate. Okay, and this is anode and this is cathode. Now if you separate, okay, if you separate this, what you will get? PNP. Okay, here this is gate, and NPN, this is one more cathode. Okay, this is anode, and this is cathode. Okay, now this circuit you draw with the PNP transistor. So that means PNP. So the arrow is inside is nothing but PNP transistor, and here NPN transistor. The arrow is outside means NPN transistor. So the connection will look like this. Connection will look like this. This is nothing but normal SCR, silicon controlled rectifier. Okay, so did you understood what is latch up? Shall I move forward? Give
So
response.
can
Yes, sir. Can you explain again?
1 second. Yeah. Actually, latch up is nothing but 1 second. Latch up is nothing but if you see the latch up. Okay, so uh, if you see the latch up, if you see for CMOS transistor, there is a low resistance path. There is a low resistance path between the VDD and VSS. Between the VDD and VSS. So why it is happening? Due to in the CMOS transistor there is a virtual transistor and resistors are there. Due to this only there is a low resistance path is there. Okay, so due to this what happens means there is a static current flow is there. There is a static current. Static current means what? Direct current is flowing from VDD to ground in the CMOS circuits. Okay, so this will lead to the damage of CMOS circuit. This will lead to what? Damage of CMOS circuit. Okay, so how it is happening means first you need to know about the diagram of silicon controlled rectifier. SCR is nothing but what? Silicon controlled rectifier. So SCR, the diagram will be like this: anode, cathode, and there is a this is the symbol for SCR, and there is a controlling gate will be there. Okay, so inside if you draw this SCR, it will be like PNP, and next like N. Okay, like this it will be there, SCR, and here gate will be there. Okay, so this is PN. So if you separate, this, what you will get PNP, and here what you will get NPN. Okay, now you can connect with the transistor. That means what, PNP, and here this is nothing but NPN. Okay, this is nothing but normal by SCR. Like this circuit will be happened in the CMOS circuit. Okay, so if you see, so normally we will do the CMOS fabrication by two methods. One is N-well technique. Next one is twin tube technique. Okay, that I will tell you in the fabrication. Don't worry. N-well technique and twin tube technique. Okay, so N-well technique means, see here. So that circuit is happening from where to where? See here, from the body, and this is R-well resistor, and this is a PNP transistor. In the N-well it is happening. N-well is nothing but it's like a substrate only. Okay, in N-well you are making this is PMOS, and this is P substrate, you are making NMOS. Okay, the how you are fabricating I will tell you. Okay, so here what happening, that means this is NPN transistor, this is nothing but NPN transistor. Okay, so there is a here this is VDD and this is VSS. Okay, so there is a static path happening from where to where, VDD to VS. This is nothing but the path, VDD to VS. Okay, so this is nothing but what, latch up. This is nothing but latch up path. Okay, suppose if you draw in a equivalent circuit, the equivalent circuit will be like this. So this is R-well, and this is substrate of the resistance of the substrate and resistance of the well, and you have PNP transistor and NPN transistor. So that means there is a short path from where to where, from VDD to supply voltage. Due to this there is a static current flows from VDD to supply voltage. So this is we call as latch-up current path. So what happens, due to this what happens, our CMOS circuit may damage. Okay, this is one problem in the CMOS circuit, that is nothing but latch-up. Okay, did you understood what I am telling, what I am trying to say?
Yes, sir.
Okay, that is nothing but latch-up. Okay, so this is one more problem in the CMOS circuits. Okay, so that means it is, so in the CMOS circuit, SCR type circuit is forming on the CMOS. Okay, SCR type is forming on the CMOS. Okay, that is one more problem.
So it is a permanent damage or it is temporary damage?
No, like when you are fabricating, when you are, disturbance is coming. Can you mute your mic? Yeah. So this is permanent or temporary, you asking, no? So here when you are using N-well technique, you are getting latch up. Okay. So for every problem there will be a solution. So to overcome this, you are going for twin tube process. Twin tube process means what? Two wells will be there. Okay, two wells you are diffusing. Okay, that fabrication method I will tell you. So in order to overcome this latch up, you are going for twin tube process. Okay, so that process you are going. So that we can avoid the latch up. Okay, so understood. Okay.
So it is a it's a fabrication problem. It's not a runtime problem.
Yeah, it's a fabrication problem. Yes.
Okay, right. Okay.
So to avoid the latch-up problem in CMOS, we can go. So these are the some steps. So we can reduce the substrate resistance, or we can reduce the N-well resistance, or we can use guard rings in the all the substrates also. We can use the guard rings means here I can use guard rings like this. I can use the guard rings also. Okay, so I can use the guard rings here. Okay, so like this I can avoid the latch up also. Okay, so see here, latch up is defined as the generation of low impedance path in the CMOS chips between VDD and ground. So when it is a low resistance is happening, there is a high current will get driven by VDD towards the ground, this may damage the CMOS circuit. This may damage the CMOS circuit. As I told you, know, this is nothing but SCR. SCR is nothing but silicon controlled rectifier. Okay, so this is the symbol for SCR, and normally PNP and NPN. So if you separate like this, you will get this circuit. Okay, that type of circuit is happening in the CMOS. Okay, it may damage, if it is N-well process, it may damage the CMOS. Okay, so how to avoid means so these are one more prevention techniques are there. By gold impurities in the substrate, we can minimize the latch-up. By epitaxial layer, okay, in the twin tube process we are using the epitaxial layer. Okay, that epitaxial layer I will show you. Okay, or place the substrate and well close, as close as possible, and avoid the feedback forward bias at source and drain, and the PMOS close to VDD and NMOS close to ground. Okay, so this is a latch up. Okay, so in the fab we'll discuss, don't worry, just I will show you the diagram how we are seeing in the fab. One second. Introduction to fabrication. Not this one. One second. Yeah. So this one, this is nothing but normally my weld technique. Okay, this is normally my weld technique. Okay, so N-weld technique. This is N-weld technique. Okay, normally, so like NMOS, so like if you see the CMOS fabrication, so you are fabricating like how you are fabricating means this is N-weld technique. Okay, so in the N-well you are diffusing P plus and P plus, and this is body, and in P substrate you are diffusing N plus and N plus. This is nothing but my body. Okay, so here my what we call this one, this N-well is acting as a substrate. Okay, N-well is acting as what my substrate. Okay, so N-well is acting as substrate. Okay, this is N-well technique. So when you are using N-well technique, you will get a latch-up problem. Okay, so you will get a latch-up problem. This is a process I will tell you. Okay, after completing the Verilog, I will tell you separately about this fab. These are the techniques how to do the N-well technique. And coming to twin tube technique. Twin tube techniques means what you need to do means here first you need to grow the N substrate, and above this you need to grow the epitaxial layer. What is this epitaxial layer means? This is also N-type material which is highly doped. This is epitaxial layer. Twin tube means what? There are two wells are there. See here, I am growing on the epitaxial layer, I am growing N well as well as P well. Okay, I am growing N well as well as P well, and in the L well I am diffusing P plus regions, and in the P well I am diffusing N plus regions. So this is nothing but my NMOS, and this is nothing but my PMOS. Okay, so by using twin tube technique we can avoid the latch-up problem. Okay, that latch-up problem we can avoid by using twin tube process. This process I will tell you. Okay, don't worry. This is about this today's session.